what you're saying?
Yes. Yeah. I doubt it. She checks her email pretty regularly. So, um, okay. So I want to show you a couple things on Canvas and we'll dive in. So this week, there are two important readings. This one, moving beyond a world, moving to a world beyond P equals 0.05. This one is a definite required must read, and the homework asks you some things about it. Nothing technical, just there's a, sort of, um, we'll talk about this as we go through, but today we're going to learn about p-values, and they've been controversial since they were invented. And so both of these papers, they come from the same issue of the American Journal of the American Statistical Association. The Greenland paper kind of just walks through a bunch of myths and misinterpretations of p-values and confidence intervals. So it's a great paper because it's aimed at students. It's a little bit convoluted. It's long, and so you can skim it, this one. The moving to a world beyond p equals 0.05, this one definitely read, especially there's a part where it talks about, all right, so it goes through this Adam statement. Accept uncertainty, be thoughtful, open, and modest. So it's basically, as we go through this week, we're going to learn about what a p-value is and how it's used to make decisions about statistical hypotheses. Most people that don't know much about p-values, but maybe have used them in practice, have kind of interpreted them as like, the be-all, end-all. Get p less than 0.05, you win the lottery, everything's fantastic, your effect is amazing. And if you don't, everything's garbage. That's not true. And so there's many, many different approaches to making a decision using the data that you have at hand. Really, if we step back from the statistical department, a part of it, drawing conclusions from your data with respect to an effect that's out there in the world. And I always forget to add that I'll do it while we're doing lecture, but there's a table that kind of lays this out, how we can be wrong in this process. So, for many different reasons, incentives that, are at play here that are beyond science, things like that. People have tended to oversell their results if they are quote unquote significant. And, that's basically the way to move forward that we can all agree on is that all statistical tests have uncertainty, so you should be thoughtful, open, and modest when it comes to making conclusions about data using the method that I'm going to go through today. So this one's a little bit, it's also kind of long, but it's much more readable. Does kind of go on and on. Then some suggestions. Oh, right. Okay, that's what it does. So really it ends around page 11. Then you probably don't have to read beyond this here, section 7. What it does is it goes through, this was a special issue in 2016 where this was the target article written by the then president of the American Statistical Association. And then they invited a number of people to write commentary. So what happens starting on page 11 is just the suggestions that the various authors give, which you don't need to go through. One of the authors here is Greenland. So it'll reference it, but all of that stuff, you can kind of skim through. Okay. And then this one's more of just kind of a reference of like, how do we interpret this stuff? It is a little bit long, so I don't want you to get confused. I'm going to give you the gist of what this one says in the lecture. And then, there's some good reference stuff in Dr. George's chapter, which I'm going to discuss that are in the slides. Right? So then homework has nothing to do with SPSS. It's going to be, I'll talk about it at the end. It's going to, incorporate, there's also no readiness quiz this week. So it's just the homework because basically we fold everything conceptual into the homework. Very much a conceptual homework. So, all right. So that's what you have to do. Would read this one before you do the homework, and then read the Greenland one, when you have time. Alrighty. Also I forgot to last week, trying to make my lectures more visually appealing than just a white screen with text on it. So I know some of this can get a little bit dry, but this week I think is more practical. And starting this week, you're gonna get some practical takeaways pretty much every single week. So we talked a lot about estimation thus far, so I'm actually not going to talk about it much today, other than sort of referencing it. But what we're going to do is we're going to dive in and learn about what hypothesis testing means in a statistical sense, right? And essentially what it means is we're testing our research ideas with data. Right? We usually, it starts with some kind of intuition or observation that we make. We might ourselves have a health concern, and we get interested in how it works, and then we talk to some experts on the topic, or we're reading about it and we get an idea. We talked about this in the first week of this kind of cycle of ideas, theories, studies, design, analysis, updating theories, right? So now we're going to zoom in on, we've done all that work. We want to specifically test an idea that we have empirically, right? So let's imagine that you're Chi-Chi, and you've read that in suburban environments, which likely have low pollution and thus, not no lead in the soil, no lead paint, that children in those areas, their average, IQ, whatever test we're going to use to measure cognitive development, the average in the suburban environments is 100 on whatever scale we're using. We think that in the city, the lead that's around, the exposure to lead is going to negatively affect cognitive development, right? So I'll ask you, the three of you, how would we test that assumption or that question, or Chi-Chi's thinking about it? What would we need? What would we do?
You mean from like a methodology standpoint?
Yeah, what are some intuitions that you might have that you'd want to do?
I guess you'd have to look retrospectively, right? Because you can't just give a bunch of lead to kids and then see how they do. So retrospectively look at what their lead levels might have been on blood testing and then see what their scores are.
Good. So you could have like a case control type design, right? It's going to be retrospective. It's going to be observational. And one way to do it, which we'll tackle next week, is to have a control group to not rely on, some population value that's out there, but actually compare directly different levels of lead exposure to each other on this variable. We're going to start more simple today. But one thing I think that Allie, you bring out, right, is we make some comparison, and then using data to make that comparison, what I'm going to try to clue us into today is at some point we have to make a decision. We have to make a decision about our data and about how it, I guess, matches up with the idea that we have in our head, research-wise. So we could distill this, sort of research question into more of a statistical hypothesis. Now, a hypothesis in general doesn't have to be statistical. I say statistical hypothesis because when we make a hypothesis statistical, we use mathematical language. So a hypothesis is simply just a statement, right, that data can either refute or be consistent with. And so it's always important to mention that a hypothesis is not a question, it's a statement, right? Because the statement has to be able to be falsifiable. That's in the philosophy of science an important part of hypothesis testing. So in statistical land, what we do is we turn what we know about the problem into a mathematical statement. And then we collect data and see if our data match up with that statement or not. And the statement we call a test hypothesis. Now, in a minute, we're going to learn that in most of the things that you do, what we do, this test hypothesis is a special name. Yeah. So we're going to say, all right, the world as it is, if business as usual, so there's no lead exposure, or there's no effect of lead exposure on children's cognitive development in Philadelphia, that this statement holds, that in the population of Philadelphia, the mean IQ or development score is 100. We write that down. We have to have something to test this against. So we also write down another statement we call the alternative hypothesis. And we use our data to make a decision about which one to go with. Now, in actuality, what we do is our data can only speak to this hypothesis. And in fact, we'll never know which one of these is true or not. But we try to get as close as we can. And so I'm going to talk about today how we do that. Okay? This is not an error-free scenario. So that's the important part. When people use hypothesis testing and they try to oversell their results, they're kind of pasting over the fact that there's never a case, no matter how strongly powered your study is, and how huge your sample size is, there's always still the probability that you've made an error in your decision. What we do when we do power analyses and we try to get big samples and so on and so forth is the best we can do is to try to minimize the long-term error rate. So today, I'm just going to give you the background ideas about this so that we can be, at the very least, literate and more critical, look at research with a critical eye. And then when you do your own studies, that you can make conclusions following the Adam statement that you'll read about, that you'll understand that there's still, accept that there's still going to be uncertainty every time you run a hypothesis test, every time you look at a p-value, no matter how small it is, there's still going to be a level of uncertainty about the effect, right? What we're really trying to do in research is, we can't, there's not like a magic ray that will tell us whether or not children in Philadelphia, that their exposure to lead causes them to have some problem with development, right? And as Ali said, the sort of gold standard for causal statements is some type of randomized control trial. In this case, it's not ethical to randomly assign children to, eat lead paint or something like that, right? We can't do that. So, but even in those cases, we're still using statistical method that is error prone. So even when we do a really great job designing a study and powering it well, there's still, we still should be a bit humble. Right? In fact, it's kind of difficult. It's really not part of statistics, the kind of level of evidence and credibility of a claim is really beyond statistics. It's more of a philosophy of science, research methods kind of thing. When do we accept, how do we evaluate the quality of evidence? But one thing that we do use is we do consider these things. We do consider the sample size, the representativeness of the sample. How big is the effect we're looking for? If we're using, a written test or a survey or a blood test, how error prone is that test? These are things that are important to evaluating the quality of research. Okay. So here's an analogy I like. There's a few different analogies for hypothesis testing, but I think this is a good one. Right? We are doing hypothesis testing in the frequentist inference realm. Right? So it's unfortunately conceptually a little bit difficult. The price that we pay for that is that the math is pretty easy. You'll find like this week we can test a hypothesis with a z-score. Next week with a t-test, which are pretty simple. You can do them by hand. Small data set, you're not going to have to. But I used to, when we teach undergrads way back, and I learned by hand. Who knows why we forced people to do that? The idea was like, working with the data, you'll get some more insights. But using this method, things actually can be computed by hand quite easily. Getting the concepts right is a little bit difficult. So here's the analogy. In the court of law, we start with a premise. We assume or presume that the accused person is innocent. And then we make a decision of guilt. We use the word prove in the courts. We want to really be careful of that word prove in science. So that's just a sort of a word we use to say we've gotten and by the way, I didn't know this until recently, that reasonable doubt or beyond a reasonable doubt is a level of a burden of proof. So you have to have a lot of evidence to be beyond a reasonable doubt. Some cases don't use that. There's like some other level of evidence, right? And all that is to say is that we start any trial with a default decision, right? The decision of innocence. Throughout the trial, evidence is delivered. And if the level of evidence reaches some point, the decision is changed to guilty. Unless, we have it on tape, the crime is on tape. There's many cases where we never will know for sure whether the person is truly innocent and guilty, yet we still make a decision, right? And these decisions are error prone. But we have all these, there's methods put in place over the years that the process works reasonably well. What we're going to call null hypothesis significance testing works in a similar way, right? The analogy is between the starting with an assumption, right? We start with something called the null hypothesis, and the null hypothesis usually represents business as usual, or that there's no effect, there's nothing going on here. So we start with that as a way to kind of be skeptical in all of our science that we do. So we assume that hypothesis to be true. We run our test and we get back sort of a level, an indication of the level of evidence, right? The level of evidence in our case is essentially something akin to how compatible our data are with the null hypothesis. If our data are really incompatible with it, then we reach a point at which our decision or our understanding of the world changes from null hypothesis is assumed to be true to we reject it and we go with the alternative hypothesis. But again, just as in sometimes in criminal trials, we may never know which one is really true. The best we can do is just collect evidence, see what the level of evidence is, make our decision at that point, and then continue to run studies, look at the effect from all different angles. And that's sort of where meta-analyses come in, and all of these different tools of combining results of different studies to kind of get this overall conclusion. Okay, so what I'm going to run us through is basically how this works, right? The sort of the way that this might work. Again, if you were to do it by hand, or what you're going to do is you're going to use SPSS to do it. So the modern so really what this was called when these methods were developed early in the 1900s under the sort of guise of statistical inference or statistical hypothesis testing. We call it null. What I'm teaching you is referred to now as null hypothesis significance testing, because essentially that's what most statistical hypothesis testing is. We have a null hypothesis for a particular parameter, and we collect data to see if our data match up with that hypothesis or not. So I'll talk about these guys: Ronald Fisher, Jerzy Neyman, and Egon Pearson. They were three guys who independently sort of worked on this problem. And the way it works is we first start by setting, like I said, what we call a null hypothesis value for a parameter. So this is important. That's the statistical hypothesis component. So this is a special type of test hypothesis where we're writing down mathematically a situation in which nothing special is going on. Right? So again, that's akin to our assuming innocence, that the person hasn't done anything. There's no evidence linking that person to the crime. In science, we start with the understanding, if we're doing null hypothesis significance testing, that there's no effect of interest. So there would be no difference between the children in Philadelphia who happen to be exposed to lead and their counterparts in the suburbs. Then what we have to do is we have to set that level of that burden of proof. Right? We have to set a point at which, a criterion at which we change our decision or not. And if we reach that criterion, then we have enough evidence against the null hypothesis coming from our data to reject it. So not to talk, this is very important. And again, this will be in your reading. Nothing that we do, unfortunately, gives us any indication about the probability that the null hypothesis is true or anything like that. All it does is could give us evidence against it. So it's like a rule out procedure. So we use probability to set that criterion. It's probabilistic criterion. These two things together, what they do is they set up what we call a test statistic. They basically, for many, many situations in which we're interested in, starting next week, we're going to learn about in many situations. They basically, these two things together allow us to derive some formulae where we take our data and we do stuff to it, and we estimate usually a couple of quantities, and those estimates form the test mathematically. Then we have fun result. I'll show you two ways that we do this. We're going to use the p-value method, but I think it's important to show you how this started. Sometimes it's the test statistic itself, so talk about what is a test statistic, or the p-value associated with the test statistic. We use those things, we compare them to our criterion. based on what the test statistic or p-value is in relation to their criterion, we make some statement or decision about the compatibility of the data with the hypothesis. I really like this interpretation. This comes from the Greenland article, that what we're doing here is we're looking at evidence in terms of compatibility of the data with the hypothesis. And then we have the extra thing, which is that when we're doing null hypothesis statistical testing. So let's say we really do think that there's something going on, that lead is affecting the children in Philadelphia. In order to show that that might be true, we want our data to be incompatible with the null hypothesis, right? So the null hypothesis is lead's not affecting these kids. So in order to illustrate that lead might be actually affecting them, we would like our data to be incompatible with that statement. So that's the weird part about hypothesis testing, is that we assume, most of the time we have a research hypothesis that we're interested in showing is the case, right? We're not actually directly doing that or testing that research hypothesis. Instead, what we're doing is we're setting up a situation in which nothing special is happening, or in which it might be the case. We're setting up a world in which there's nothing special going on. We collect data in which there may be something special going on, and we see if that data is compatible with the world in which there's nothing special going on. If it's incompatible with that world, then we say, ooh, there may be something special going on. If it's compatible with that world, then we say, well, we don't know, it's inconclusive. It doesn't look like lead is really having its effect, so on and so forth. The reason it's kind of weird like this is because, in fact, in the larger scheme of things, statistical hypothesis testing was actually more the easiest place for it to be applied is actually like in factories. So let's say you have a lot of items, and your assumption. So they're coming off the what? I don't know. We're making I have my spoon. Okay, so we're making spoons, and we're in the spoon factory, and the spoons are shooting off the assembly line, and we're in quality control. Okay? We need to test whether or not the whole lot of spoons is good or not. So what do? We can't look at every single spoon. That's going to take forever. If we do that, we have handmade spoons and they cost a lot of money. We don't. We have machine-made spoons. We want them to be, low cost, so on and so forth. So where this procedure works really well is when our default hypothesis is all the spoons are perfect, right? Nothing wrong with any spoon. That's the null hypothesis. What do? We take a sample of spoons. Maybe we have some measurement of how long they're supposed to be. We take the sample mean. If the sample mean is consistent with the spoons all being good, we say, great, they're good. If the sample mean is inconsistent, if it's too far away from what it should be, we reject the whole lot. That's actually where this works quite well, this type of testing. What scientists did pretty quickly in doing all that was realize, oh, that sort of all the spoons are normal situation could actually represent the null hypothesis of skepticism about an effect. And then we collect data and see if the data matches up with our skepticism or if it refutes our skepticism. So it's a little bit nutty. And that's part of the reason why, and in order to get that level of understanding about it, you tend to need to, I will say, so I'll just say this. I went to, did my graduate work in psychology, did a lot of quantitative psychology, a lot of statistics for psychology. I really only got that understanding of things in the last 5-10 years by reading on my own and really digging into the problem. So it's a thing that's not being taught or wasn't being taught. So now part of the reason I'm really harping on it this week is we're hoping to avoid that in the next generation of PhD folks across science, is like to reveal the fact that this is an error-prone process and that's okay. And then, of course, you have this sort of nefarious thing where, unfortunately, you'll read about this and Stephanie works in clinical research, right? You're in clinical research, Steph? I forget.
Oh, not now. I'm not.
Oh, not anymore. Okay, right. So many people that are in clinical research could attest to this, might have come across PIs that are much more interested in having an effect, right? And journals being biased to publish significant results. That really had a unfortunate effect on some of this stuff. So anywho, that's the analogy. That's the concepts we're going to go through. Sound good? Sorry, Steph, I got confused.
Okay.
Alrighty. So I'm going to talk about the two ways that we teach this, and sort of this is actually, again, the method that we use today is an amalgam of these two very similar separate methodologies developed in parallel in the 20s and 30s. The Neyman-Pearson procedure is based on statistical decision theory, and it's pretty simple. Right? We state the hypothesis. We derive what's called the sampling distribution of the test statistic. We did that last week. We work out, well, what, if we're testing a sample mean, what is the variance of sample means across samples? That helps us write down the test statistic. We set an alpha level. So what is alpha? Alpha is our criterion. It's our statistical criterion. It's a probability value. And we decide on it before we collect the data. And what it does for us is it basically sets up a point, or really a value that your sample mean has to reach in order to change the decision from accept the null hypothesis to reject it. Two things that are important that you'll read about is many people believe that alpha is the probability that a null hypothesis is true or false. That's not true. Right? It's also not the probability that a result occurred by chance. Right? Simply what it does is it's a point on the sampling distribution where we split it into two regions. And I'll show you this pictorially in a minute. Right? So what this does is it sets up two categories that your numerical results can fall into. They can fall into the accept region, which is a bunch of values of test statistics. So today we're going to deal with a z-score as a test statistic. The accept region are all these z-scores that are on one side of alpha. And the reject region corresponds to the rest of the distribution. So we do all that work, and then, so this is all the conceptual work. Then we compute a z-score, which takes 5 seconds as long as we have the data. And we see where it falls. Which region does it fall into? Right? So let's see this with Chi-Chi's results. Right? So we know that in the population of folks that are not exposed to lead, the average cognitive development score is 100. So we're going to set that as our null hypothesis. Right? That's the first step here. Then what we need to do is derive the sampling distribution of the test statistics. So last week we worked out that if you're, let's say our sample size is 144 people, okay, that's large enough to use the normal distribution as a model for a sample mean. So we know that for our data, the probability distribution is the sampling distribution of the mean. And what we need to know about is what's its standard error. Okay? So what we're doing this week is called a one sample z-test. It's not something that you would do very often nowadays because we have access to so much data. We do a retrospective case control where we'd have a control group, right? But in this case, we're going to go very simple. We have information. So the downside of a one sample z-test is you need the population mean and the population standard deviation. So with IQ or any type of norm reference test, usually we do know that, right? It's written in the manual. So we're going to use those values to set up our test statistic. So standard error in this case is the standard deviation of these test scores divided by our sample, the square root of our sample size, right? So 25 divided by 12, it's about 2.08. So again, what does this mean? This means that we would expect, if the null hypothesis is true, that any sample of 144 children should have a sample mean close to 100 within about 2 points on either side. And as we get further and further away on the scale of 2 test score points, our data are more and more incompatible with the null hypothesis. Here's something that you're going to read about. This magical number 0.05. Okay? We often set alpha to be equal to 0.05. Why do we do that? It's a nice round number. Okay? And what it does for us is alpha is setting the long run error rate. So back to the factory, back to the spoon factory. Okay? If I set alpha at 0.05 when I do my spoon test to see if the spoons are good, what I'm doing is I'm saying, if I test spoons every day, 1 out of the 20 of the tests is going to be incorrect. I'm going to make an incorrect decision. So 95% of my decisions are going to be correct. So 95 is a nice round number. It's pretty cool. And the reason that it sort of became commonplace is just that people just got used to it. It also represents a criterion that works well across different sciences. Again, you'll read about the fact that, for example, it works very well in the social sciences and medical sciences where, even with blood tests, there's still a fair amount of measurement error, especially when we're using survey data, stuff like that. In situations in the physical sciences, physics, they set alpha at like 0.001. Their alpha values are very small. Their criterion for rejecting null hypothesis is much higher because their measuring devices are usually much more precise. The measurements they're making are very precise. So it's a nice compromise. What does that do for us? It does the following, okay? So here, by the way, you can make these fun little normal curves. A few of them you saw last week. You see them in the text at this really cool page, right? So what have I done here? Okay? What we're looking at is the standard normal distribution, right? Standard normal distribution. Normal distribution with 0 as its mean and 1 as its standard deviation. Okay? I can find, and this is what was done way back, is we figured out, well, okay, on the standard, so the normal distribution is the model, the probability work model we're using for the sample mean, right? So what I do is, and when we set alpha at 0.05, what we're doing is we're asking ourselves, well, what point on the normal distribution separates 5% beyond that point and 95% on the other side of that point? So we set up the accept and reject regions. Oops, I don't have them on this slide. We'll come back to that. Now, why do we use the standard normal distribution rather than a normal distribution with a mean of 100 and a standard deviation of 2.08? Well, basically they're the same. And it's a lot easier for computers and before computers for people to work with the standard normal distribution. Whatever's true of the standard normal distribution is true of any other normal distribution. We transform between them using the z-score formulas. So what does that mean? It basically means all we need to do is get a sample mean, and we have the third in the 3 sets of things that we need to compute a z-score. We compare our z-score to negative 1.645, and that's our criterion. If it falls on this side of negative 1.645, we reject the null hypothesis. If it falls on this side, we don't. So let's see what we did there. We basically, we haven't used this information yet, but this helped us set up the sampling distribution. We said, okay, the model for our experiment is the sample mean is a normally distributed test statistic. We don't want to work with the scale that our data is on. We want to work with the standard normal because it's easier. So we pick out a value that we have to beat, right? And then we go, and we pick out that value using the alpha level. When we change alpha, what we're doing is we're sliding this criterion around. Now, another thing to notice is we've only got one part of the distribution highlighted in red here, right? The low part. Later on tonight, I'm going to talk about how what we're doing now first is we're learning what's called a directional hypothesis test. We're predicting a direction, right? We predict that, or it's kind of baked into the statement of the problem that children in Philly are going to have lower development scores than those outside of Philly. So we're really only interested in results down here because these would be results in which our mean is lower. Most of the time, we don't do these one-tailed tests with this type of data. We would do a two-tailed test, which I'm going to discuss. But the important things here are sampling distribution is normal. Alpha, we get to pick what this is. By default, in this course, we're going to leave it at 0.05. You can change it around. You can read about that. In a Neyman Pearson model, what that does is that helps us pick a point on this reference distribution that we're going to compare our test statistic to. So you guys can try this, right? We already know that the standard error is 2.08. We know that the population mean is 100. And now let's say we test 144 kids in Philly. And let's even say that they've been exposed to lead. We know that. The sample mean is 97. How do we transform that into a z-score? So for a sample mean, we take our sample mean, subtract from it the population mean, and divide by standard error. So we have all three of those values. The only one we would have had to compute, well, there's two of them, right? With this one we get from prior knowledge. So in a one sample test, prior knowledge gives us our mu. Our data come from in the form of the sample mean, and the sample size helps us get standard error. Right? But we need to know what the population sigma is. So we do all these computations. What is this telling us? What is a z-score? In actuality, it's basically taking the raw difference, right? So we can clearly see that on average, our 144 kids are 3 units below the national average. That's a descriptive result. Okay. To draw an inference, what we do is we bring in, well, relative to normal sampling variation under the null hypothesis, what's that in sort of that relative ratio form? Well, it's negative 1.44. Okay. So now this value, we go back to our sampling distribution, to our reject region and our accept region, and we ask, right, where are we? So with this This is our data. This is the evidence from our data. This is the test statistic. Where does it fall? Does it fall in the accept region or the reject region? What do you guys think?
It falls in the accept region because it's outside of the pink zone that you've got there.
Right, this blue line, which is the dividing line, is negative 1.645. Negative 1.44 is around here. So our decision would be, in this case, accept or retain the null hypothesis. Okay? We might say something like, okay, the sample mean is clearly 97, it's not 100. But that's not enough statistical evidence to reject the idea that lead really isn't having any effect. Okay? Why is that the case? So if we think back to last week, sampling theory, we could replace the 0 and -2 here with 100, and then -2 would be like 100 minus 4, something like that. All right. So basically, we're within sampling error. Our sample mean is still within the set of results that would be consistent with the null hypothesis due to the fact that samples from a population tend to vary naturally without anything funny going on. So now notice, we still can't make a conclusion about the effect for certain. All we can say is our evidence doesn't support any effect of lead. We can't talk about the probability that there is an effect or isn't effect. We can just say what our data, in this process, what we're doing is we're looking at whether our data are compatible with this null hypothesis or not. If they're compatible, we can't reject it. Business as usual, doesn't seem like there's evidence for an effect. If we can reject it, right, we have evidence against the null, or we start to, depending upon who you talk to, you can claim, yeah, we're getting it to the point where we do have, statistical evidence for the effect. So basically, what would we have needed to have gotten here? In most cases, 2 standard error units is often what you need to get to a reject decision with 0.05 as your criterion. So it would have been better, so 2 standard error units means 2 times 2.08, so about 4. So if we if the sample mean was like 96 or 95, our z-score would have been lower. It would have been over here, and we would have said, yeah, we have enough evidence, right? So a test statistic, which is what z is, next week we're going to learn about t. It's a function of our data, and we use that because it's easier to derive a probability distribution for that test statistic. So in this case, the probability distribution is normal, and we can use what we know about the normal distribution, which is that 5% of the distribution is at or below negative 1.645. So far, so good. All right, so now you guys, since you're in the 21st century, so I had to do this, to look at the table in the back of the book and all that stuff. If you took stats courses before, you might have had to look up z-scores in the z-table and get the probability. We don't have to do that anymore. Okay? We get to use p-values. They're routinely computed by all the computer packages. What are they? They were sort of developed in parallel, and there was a lot of back and forth banter between Ronald Fisher, who was English, and Jerzy Neyman and Egon Pearson, I spelled his name wrong, who neither of which were born in America, but were based out in, I think in Berkeley, out in California. Fisher argued that Neyman and Pearson's method was sort of limited by the fact that, like, here all we could say is what side of the fence we're on. right? In the Neyman Pearson method. Okay? Fisher wanted to be able to quantify the level of evidence specifically using a value that we've come to know as the p-value. Okay? What is the p-value? Okay? Well, let's look back here. It's a probability. Okay? We tend to think of it as what we call a tail probability. So here, what we have to do when we define a p-value is talk about what an extreme result means. An extreme result in this case would be a result, a z-score that represents a test statistic way far away from the null hypothesis. Okay? So the extremes of a normal distribution are in the tails, where the line gets really close to the x-axis, meaning that these are scores that are very, very low probability. They don't occur very much. So what a p-value is simply describing the probability that you would obtain a score at or below that point, or at or more extreme than whatever point you're at on the curve. Okay? So for example, if our z in this z-test had equaled, instead of negative 1.44, if it had equaled negative 1.645 on the dot, our p-value for the test is actually 0.04998. It's not exactly 0.05, but it's pretty close. So alpha itself is a p-value, in a sense. Right? It's a probability. So p-value is the probability of obtaining the result that you have, or one that's more extreme, if the null hypothesis is the correct model, if that's true. So smaller p-values means less compatibility with the null. That's all it is. It's just an extra piece of information that we get about our test statistic. Right? So again, p-values relate to alpha, such that if alpha is 0.05 in a study, the p-value of any test statistic in the reject region will be 0.05 or less. So the Neyman Pearson method is computationally simpler. We don't have to get a p-value. So it wasn't until computers came along and made it easier to use them that we used them. Generally, they're reported to 2 or 3 decimal places, or sometimes 1 or 2 significant digits, because sometimes we have a lot of zeros there. Sometimes they're really small. So let's take a look at it with the same data. Okay, so the situation is pretty much the same. We set alpha. Okay? This time we make it explicit that alpha is now going to be a p-value criterion, right? So the difference between using p-values and using what we call critical values, that's what 1.645 is. We call it a critical value. A critical value is a score that is a number the test statistic could take, so a z-score, whereas a p-value is a probability. So in using the p-value method, alpha basically is a threshold for the p-value of the test. So basically, we need to have our p-value being less than or equal to 0.05 if we use alpha 0.05. We still have to compute the test statistic, and then we go one step further, which is what we compute the p-value, the tail probability. So this is, again, what we call a one-tailed p-value. Okay? So our test statistic was negative 1.44, right? That's the z-score we got with our sample mean. That represents essentially how far away from the null hypothesis mean is our sample mean in units of standard error. So it's 1.44 standard error units below 100. In probability world, that point on the normal distribution has 0.07493 of the probability below it or more extreme, and about 92% above. So this p-value does not reach the 0.05 threshold. And so again, we come to the same conclusion. So these methods with the same alpha, if you set alpha at 0.05 and use either method, they give you identical results. What you get with this method, the p-value method, is essentially you get to use your own alpha then if you're reading the study. So you might look at 0.07 and say, oh, that's close, right? Maybe there's something going on there. It just didn't have enough people, or they used a messy measure, right? Because researchers are free to use 0.10, 0.0658, doesn't matter. By convention, 0.05 is nothing special about it. It's just what we've picked. It's not a magic number. And again, what does it mean? It means that in the long run, if we did this study over and over and over and over and over again, right, using alpha 0.05, we would only make a mistake. Our decision would only be a mistake 5% of the time or less. So let's finish up just talking about these non-directional tests, and then we'll take a break and then finish up. So I began with the directional test because it's easier to deal with, right? We have a directional hypothesis. We think the children are going to be negatively affected by the pollution, so their development scores will be lower. And so we set up our test statistic and our p-value to focus only on one of the two tails of the normal distribution. In practice, we almost always, by default, unless we really have a lot of reason to do so, use what we call two-tailed tests. In a symmetrical distribution, so the normal distribution, the t-distribution that we'll use next week, and the binomial distribution too is symmetrical. A two-tailed p-value is just 2 times the one-tailed p-value, right? So for our previous result, the one-tailed p-value for our result is 0.07439. I multiply that by 2, I get something on the order of 0.14 or 0.15. That would be my two-tailed p-value. So two-tailed p-values are generally always larger than one-tailed p-values. Why would we choose one or the other? Again, some people have called for using more one-tailed tests. The two-tailed tests are more conservative. And so if we want to be more skeptical, we use them. And generally, we want to be more skeptical, especially when we are just starting out in an area, trying to collect some initial evidence. You'll see later on in the course, though, we don't always use two-tailed p-values. In instances of chi-square tests, F tests, the sampling distribution is not normal, it's skewed, and so we only do one-tailed test. This basically matters because some statistical programs will give you the one-tailed and the two-tailed p-value, and it's important to know which is which. All right. Let's take a break, then we'll do another example, this time with two-tailed p-values, and then talk about fun stuff like type 1 error and power, which really get us into even more fun conceptual land. So take a break, come back at 6:35. Good. Okay. So let's press ahead. So now we've, taken our time and gotten through p-values and test statistics, null hypothesis, all that stuff. And by the way, we're going to practice this through the rest of the course. Basically we're going to just learn a bunch of different hypothesis tests, when to use them and how to do them correctly, how to be aware of the errors that you might be making, the uncertainty, all that stuff. So it's okay. Again, it took me many years to really master this material where I could even come up with good analogies for it. So, all right. So here's an example with a two-tailed test. I think I was going to flesh this example out and then I just forgot, but that's fine. And we don't have to do a full example. It's analogous to the previous situation. Essentially, what you would do is as follows. So again, let's say this time you're testing the safety of a new drug. The drug is for something. Who knows? I just saw a commercial for Obsolora when I went downstairs. I don't even know what that does. I just know the person in the commercial looks very happy. So maybe I should be on that drug. I don't know. But let's just say you're in safety trials and you don't know if this drug might affect blood pressure in a particular way. You hope it doesn't, but you want to test whether it does or doesn't. So you would be interested in, again, results that are incompatible with the null hypothesis, both in the positive direction, meaning spikes in blood pressure, or in the negative direction, blood pressure that's too low, right? Lowering it. And so that's the world in which a two-tailed test becomes very helpful. All it does is we leave alpha the same. Essentially what we're doing now is we're splitting alpha into the lower and upper tails. So on the Z distribution, we get two new critical values. Because essentially what we're doing is we're trying to find, so with alpha 0.05 two-tail, we need to find the Z values that put 2.5% down here, or 0.025 down here, and 0.025 up here. And since the Z distribution is symmetrical, that's negative 1.96 and positive 1.96. So very close to 2. That's why I was saying that 2 standard errors rule is a good kind of rule of thumb in these types of tests, which have been generalized into what's called the walled test, which we'll talk about when we get to regression, for regression parameters. But basically, if your test statistic is 2 times as large as your standard error, you're generally going to have a low p-value, a low two-tailed p-value. So in the critical value approach, you would simply just compare the negative 1.44 to these 2 new critical values, right? There's still reject region and accept region. Now the reject region is split into 2 possible scenarios for rejection, right? Blood pressure that's way too low, blood pressure that's way too high. In the lead example, we could have left it two-tailed, which, we're testing whether IQ is different in Philadelphia. Maybe children have higher IQ, and we might say, well, lead is good for IQ, which we wouldn't, but that's the idea. The p-value interpretation works the same. We still compare the p-value to 0.05. It's just that the p-value is computed differently. The p-value is just computed differently. You don't need to even worry about how it's computed. So next week it's going to matter because you're going to be doing t-tests, and by default, I think SPSS gives you the two-tailed p-value, so that's the one you're going to use. Okay, now let's dig into some more concepts. So we've covered alpha. Alpha is basically a probability, and we use it as a cutoff, basically as a place where a criterion for our decision. Again, the reason it's set at a particular level is it regulates the probability of one of the 2 types of errors in statistical hypothesis testing, which is alpha regulates the rate of type 1 errors across repeated uses of the same type of data, right? So if you were to for whatever reason, do this study with 144 children, 1,000,000 times, and you ran a hypothesis test all those 1,000,000 times, keeping alpha at 0.05 means that 5% of your decisions across that span are going to be incorrect. And sorry, 5% of your decisions are going to be type 1 errors. I should have said it that way. Specifically, alpha regulates the probability of a type 1 error in the long run. But in the long run is important because it doesn't mean that there's a 5% chance that our particular result is an error. Right? We can't do that with frequentist probabilities. Our result is either an error or it isn't, 50-50 chance. So what alpha does is it, just like in the spoons example, it over repeated tests of the spoon length, using alpha 0.05 regulates the probability of type 1 errors across all of those tests. And if we put it at 0.05, 5% error rate. If we lower it to 0.01, 1% error rate. If we keep going down, we keep lowering the error rate. You can think of type 1 error as akin to a false positive in a medical diagnostic test if you want to. It's not a perfect analogy, but it's helpful. So type 1 error happens when our decision is to reject the null hypothesis. Our data seem to be incompatible with the null, so we reject it. But in actuality, the null hypothesis is true. So in a medical diagnostic test, again, our decision is to, if we assume that the null hypothesis in the test is negative, right, that you don't have the problem, then a type 1 error is a false positive. Because p-values relate to alpha, they're sort of somewhat related to type 1 error, but they are not themselves tied to the probability of the type 1 error. So by choosing an alpha, we're setting the error rate long-term, which we wish to get as low as we possibly can. So in that specialist issue of ASA and other things that went around at that time, there was a suggestion, well, why don't we just lower alpha? Why doesn't the convention become 0.001? Well, the reason that isn't ideal necessarily is because as we continue to make alpha smaller, we increase the likelihood or the probability of the second type of error. We can make very creatively named type 2 error, and that is akin to a false negative in the medical diagnostic world. A type 2 error is we have decided to not reject the null hypothesis. We've fallen in the accept region, but in the real world, the null hypothesis is actually false. So type 2 error, null hypothesis is truly false, but our decision was to not reject it. In more technical texts, type 2 error rate is denoted by beta. Type 1 error rate, alpha, we get to choose freely. We get to choose what it is out of thin air. We can just say it's 0.05. Once we do that, and once we set the sample size for our study, the probability of a type 2 error, beta, is also set. And beta's inverse, the probability of not making a type 2 error, is a very, very important statistical concept called power, which we're going to talk about in just a little bit. So as a compromise, again, this is why 0.05 and 0.01 work pretty well, especially in social research, medical research, where, again, things are still messy. Measurement is messy. Sample size is sometimes small, so on and so forth. So by keeping alpha a little bit higher, we run the risk of false positives, but we don't miss things, right? We keep the false negative rate as low as we can keep it, okay? Because we certainly don't want to fail to detect an effect of lead, for example, right? When there is indeed one. That's no good. Right? So that would be a type 2 error. So we may have made a type 2 error in our situation because we decided not to reject the null hypothesis. Our data were compatible with it. Right? But in actuality, lead may be affecting children's IQ. We just failed to detect it with our data. You can also make the analogy to guilty, not guilty. This one works even better. Doesn't really matter. The important thing to understand, and this is where the concepts become annoying, is there is a goal, sort of a ground truth out there in the world. The null hypothesis is true or it is false. We, again, can never know for certain what the truth is. All we can do is make conclusions from our data. Notice our conclusions are not null hypothesis is true, null hypothesis is false. Our conclusions are we fail to reject the null hypothesis or we reject it. So if our conclusion is fail to reject and the null hypothesis is true for real, we have not made an error. If we reject, but the null hypothesis is true, that's the type 1 error. If instead it is the case that the null hypothesis is false, so lead does cause children's IQ to go down, but we got our result, which is we failed to reject, then we've made a type 2 error. Right? Of course, we haven't made an error if indeed our data are compatible with this situation of the null being false. So again, this takes some time to get used to. The point is again, we live in this world where we don't know the truth. So all we have are we have this decision to make, and essentially, and alpha regulates the probability that we make this type 1 error. Right? We get to set that. We get to choose what this error rate is. Once we choose it and set our other design elements, the probability of a type 2 error is baked in. So, there's a couple other things I'm going to talk about, and then we're good. So, I'm not going to harp on this. People really have gotten to be not liking the term statistical significance. It's a fine term as long as you understand what you're saying when you say it. So if you say a result is significant, doesn't mean it's important. It just means that it's met the criterion for rejection of the null hypothesis. Doesn't make it special or anything, right? Still could be an error. More and more, we're trying to push for more uncertainty in what we publish. But of course, in science, at the end of the day, we have to make a decision at some point, right? That's what our brains are kind of made out to be. So your readings this week are just meant to kind of, consider this stuff on your own, right? Are we too interested in, dichotomania, making everything a binary decision? How much can we tolerate uncertainty in our research findings, so on and so forth? So basically the conclusion to draw is a p-value is a tool for making a decision about a hypothesis. P-value is not an effect size, right? So just because there's a small p-value in a study doesn't mean there's a big effect, right? Simply just means that your study had a lot of power, usually has a large sample size, or that the effect that you're looking for is very large. So the idea that p less than 0.05 is like you're done and it tells you everything is just not true. So that's, again, we're trying to emphasize this, right? It's an important piece of our decision-making apparatus, but in and of itself is not a measure of effectiveness. couple other things you'll see in the Greenland article about what a p-value isn't. It's not the probability that the null hypothesis is true. It's not the probability of replicating a result. It's also not the probability that the result is a type 1 error, right? A p-value is simply just the probability of obtaining our result or one that's more extreme if the null hypothesis is true. So it's a probability value on the null hypothesis distribution. If it's low, our data are not compatible with the null hypothesis and we can reject it. But it's not telling us anything about the truth or falsity of it. We just use it as a decision-making tool. All right. So there's one more concept in hypothesis testing that's important, but before we get to it, I do want to make this point because it's important, and you're going to be constructing confidence intervals or reporting them. You did last week and each week. So confidence interval is usually the way that we represent effect size. And one place where it's important is in it could be used basically in lieu of a p-value. Confidence intervals are defined using alpha, right? They're often in statistical tests, they're defined this way, right? Or it should be not 101 minus alpha, sorry. Right? So if alpha is 0.05, a 1 minus 0.05, right, is 95%. Right? A 0.05 alpha test can also be constructed using a 95% confidence interval for the sample mean. Here's how you use confidence intervals for null hypothesis testing. If you construct a confidence interval for your sample result and the null hypothesis value is not in that interval, then it is a reject decision at whatever alpha level you used for that interval. So 95% confidence intervals are used a lot because they correspond to a test with a 0.05 alpha level. And then, let's see what do they represent? They basically represent those two demarcation points on the distribution, right? So I literally use plus and minus 1.96. The difference, right, is instead of my distribution being centered at 0 at the null hypothesis value, when we make a confidence interval for a sample mean, we're looking at that population. Right? So the lower confidence limit becomes, right, sample mean minus 1.96 times standard error. That puts it back onto the level of IQ, right? So our lower confidence limit in this case would be 92.92. Our upper confidence limit is 101.08. And as we can see, 100, which is the null hypothesis value, falls in between those two limits. And that agrees with our results. So what a confidence interval basically is we use normal distribution theory, not for the null hypothesis, but now for the alternative hypothesis. Right? What is, again, the range of plausible values for a sample mean for our result? Right? If the null hypothesis value is in that range of plausible values, then the null hypothesis, we don't have enough evidence against it. If my confidence limit, the upper one, was like 99.08, that we would have seen in our other tests that p would have been less than 0.05, where we would have rejected using the critical value method. So all a confidence interval is two limits where your test statistic is in the middle and you're marching out 1.96, almost 2 standard error units away from it to get this inside of the distribution rather than the outsides. And this picture is misleading because we see 0 there. But what we're doing here is we're making 0 represent not the null hypothesis value, but the value that we found. So now 0 represents 97 rather than 100. So again, you don't have to compute confidence intervals. They're fairly straightforward if you have the bits and pieces, right, that you need. Again, the 1.96 comes from the normal distribution. It's there to transform scales. So our last topic then is the final piece of the puzzle with respect to the errors that we can make, and that is statistical power. So there's a couple different ways to conceptualize it. All of these statements are relatively equal or equivalent. So first is power is the probability that the results of an experiment or study will allow rejection of the null hypothesis if the independent variable has a real effect. I hate that one because it's like a little bit too wordy. Okay? This one's a little bit better. Power is the probability that the results of an experiment will allow rejection of the null hypothesis if it's false. So if it's false, usually the independent variable has a real effect. I also like it as the probability of making a correct decision when the null hypothesis is false. When we're designing studies, and that's really the only time we have control over statistical power is when we design a study. Once we've collected the data, that the power is already predetermined. Okay? We try to make power as large as we can. So I want you to look at this. This actually comes right from Wikipedia, and it's I was looking for good images of this last night, and I was actually should be surprised because Wikipedia does a nice job with math. So what happens when we are computing the power of a test is the sampling distribution 1 here in blue. This represents our null hypothesis, right? So in in our example with lead, this distribution represents the distribution of means on the z-scale when the null hypothesis is true. What we have to do to define power is we first have to set our alpha level, which we've done. And then we have to figure out where the alternative hypothesis distribution lives. So this second sampling distribution represents what is the case if the null hypothesis is false, right? It's super made up, right? It's not just, doesn't exist. It does exist, it exists mathematically. What you have to work out, say, when you're planning a power analysis for a study, is you need to figure out what should be the distance between the two centers of these two distributions. Okay? So we always center the null hypothesis distribution at 0 on the test statistic scale, on the z-scale. The other distribution, where it lives, depends on the size of the effect. So if this case illustrates what would be true if, like, let's say instead now we're looking at lead and some type of score that we have that it's encodes something about the child's risk for health problems. If the null hypothesis is true, then there's no risk for health problems. If it's false, then there is a risk, and we have to figure out how big that risk is by figuring out how far away, or how big of a difference in sample means would there be. Power is then computed as the proportion of the sampling distribution representing the alternative hypothesis. It's the proportion of that distribution beyond the critical value on the first one, which is, again, kind of weird. And so that's what you're seeing here. So the power of a test like this would be probably a little bit more than 0.5. That's actually considered low power, lower-ish power. Power of 0.8, which would be the case if you moved this red curve out over here, so there's less overlap, that would be higher power. Remember, beta is the probability of making a type 2 error. Power is 1 minus beta, basically the probability of not making a type 2 error. The main way that we can increase power, the thing that we have under our control, is sample size. So generally, an increase in sample size is going to increase power. Why? These are sampling distributions with standard errors. Okay? When you increase sample size, remember where sample size is in the formula for standard error. Do you guys remember? Is it in the numerator or the denominator? I know you don't have to memorize formulas, but think back to what we did for Chi-Chi.
It's in the denominator.
It's in the denominator, and I don't think right? But if you recall, okay, standard error of X bar equals sigma in the population divided by square root of n. So when we increase n, we make the standard error smaller. What does that do? It makes these two guys thinner, so less overlap between these two distributions. So less overlap between the distribution that represents the world in which there is an effect and the distribution that represents the world in which there is no effect. Okay? So when we increase sample size, it makes those two distributions thinner, thus they overlap less. Okay? What does that mean practically? When there's less overlap between these two distributions, there are fewer results that would fall on both of them, right? So take a look at this overlap. These are probability distributions. The x-axis is possible test results, right? Look at all of this entire set here. Actually, almost half of the sample means that are compatible with the alternative hypothesis are also compatible with the null hypothesis. That's a low power scenario. It means that it's very difficult for our data to show us what's really going on. As we make these distributions skinnier, there's less and less overlap. There's fewer and fewer results that are compatible with both hypotheses. So sample size allows us to regulate how thin or how much overlap there are for a fixed distance between the null hypothesis mean and the alternative hypothesis. So by increasing sample size, we decrease standard error, which makes these distributions skinnier, less overlap, more power. Power can also go up or down with effect size. So power is proportional to effect size. It's inversely proportional So power is proportional to both. Power goes up or down with effect size and goes up or down with sample size. So as sample size goes up, power goes up. As sample size goes down, power goes down. As sample size goes, or as an effect size goes down, so does power. What does that do? Let's keep these distributions as wide as they are. Effect size separates how far away the centers are from one another. So smaller effects means, again, the two are going to get closer and almost overlap fully. Meaning, again, almost all of our test results are compatible with both, which makes it difficult for us to make the right decision. Can you see? It's probably hard to see. I can see it because I've looked at these charts for years. How alpha gets into this, comes into play. Alpha is regulating the size of these blue shaded areas. As we make alpha smaller, it moves the blue shaded area further into the alternative distribution. So as you decrease alpha, basically making it harder for your test result to lead to a reject decision, power is going down. Why? Power is going down when you decrease alpha because generally you're going to be making more decisions to not reject the null. So the more decisions that you make to not reject the null hypothesis, the greater the probability that you're making a type 2 error. So again, what is statistical power? Power is represented by the pinkish shading here. It's a probability. It's the probability that you correctly reject a null hypothesis. So it's the probability that you make a correct decision when your decision is to reject. It's also the probability of not making a type 2 error. We generally don't have control over sizes of effects. The thing that we have control over in our studies is sample size and alpha. And so, and generally alpha, we don't want to buck convention a lot. So that's usually kind of fixed at 0.01 or 0.05. So where power comes in practicality is when you get, for example, towards your dissertation, you're going to want to justify the sample size often with a power analysis. In general, in clinical research and really any research with people, the more the merrier. The greater the sample size, the better. However, again, in special populations or with patients or with drug development, you don't want to go out exposing people to stuff that they don't need to be exposed to. So what a power analysis can do for you, right, is it's a procedure before you run a study to determine the power of a test. Usually what the end result is, you're trying to get indication of what is the smallest sample that I can use and still keep my type 2 error rate low, keep my power high. So I've given you this link to a handy computer program that's been around for a while. It works really well on all systems. And it's what a great many people use this is very common in grant proposals, and so on and so forth. The FDA is interested in it when you're doing trials. It's an analysis whereby if you specify alpha, the effect size of interest, which usually, you're basically trying to figure out, well, what's the clinical effect, the smallest relevant clinical effect that I want to be able to detect confidently. You have to figure that out via research experience, looking in the literature. And how many groups you want or what design it is, you can get a sample size. It can be computed for you. So let me show you what this looks like. I haven't used it in a while, so it'll be fun to revisit. This is G-Power. It's got all kinds of things going on. So It has all different types of families of tests. So in advance of next week, where we're going to be doing all types of t-tests, but one that's very common is the two independent groups. So in this case, imagine that, again, I'm doing my drug safety study, and one of my groups of people get a real drug and the other gets a placebo, and I'm simply just looking at some safety thing like blood pressure. Right? You see that tails is one of the options here. I'm going to choose 2. Then I have to choose an effect size. You'll see it's D. Often the effect sizes that you have to use in this program are standardized. So D is Cohen's D. We'll learn about it next week. 0.05 is a medium-sized effect. So I'm going to go ahead and ask for 0.2, which is a small effect. You can see alpha is set by default to 0.05. I can change it. Power is set to 0.95, which is really high. And then we also have an allocation ratio, N1 to N2, which I'm going to say is like 1.56. What does that do? This gives me the opportunity to have the groups to be slightly different sizes. I'm going to plot for you. So what this shows us is, for a number of different levels of power, what is the total sample size we need to detect a very small effect size? Well, it turns out it's got to be pretty large. Check that out. So 0.8 or 80% power is what's kind of considered, along with 0.05, to be pretty good, good enough for our purposes. And so what is a 0.8 power? It corresponds to a 20% chance or 0.2 probability of making a type 2 error. So to achieve 80% power, we'd need just over 800 people in our study, roughly about 400 in each group. Now, watch what happens when I change the effect size. Change it to a medium-sized effect, 0.5. Now, I don't need as many people. Right? I only need about 120. Why is that? Because the distributions are moving further apart now, right? The size of the effect is now bigger, easier to detect through the noise with a smaller sample. As I keep increasing 0.8, which is considered a large difference between two groups, I only need about 50 people total in my study. So that's how power analysis is used in practical stuff in research. It's impossible to know what the true effect size is. So often we have to estimate it, or what you do is, you look at a range of effect sizes. You look at these, plots like this, and you make your best effort to recruit. Sometimes, you're interested in a small effect and you're just not able to recruit that many people. So it's good to be able to say that before your study is run, and you might decide, I'm not going to run it. Right? I need too many people, or it's too dangerous, or whatever. But so as you can see, changing effect size, making it go up, larger effects, we can achieve high power with fewer people. And then if I was to drop the alpha to 0.01, right, now I'd need some more, right? My sample size goes up, so on and so forth. Okay? So statistical power related to sample size of the effect, and alpha. We have a higher powered test when our sample size is large, and or our effect size is large, and or our alpha is, sort of closer to 0.05 than to 0.01 or 0.001. Okay, so I just collected these all onto one slide for you, just to kind of have them around. So we're going to be dealing with these concepts for the rest of the course. So each week, I'm going to teach you, okay, for this particular research scenario, we've got these two groups. We want to know, are they different in some way? Did the intervention that we planned have an effect? We will set up a null hypothesis and an alternative hypothesis. Unless I tell you specifically otherwise, we will keep alpha at 0.05. It'll be very clear if we change it. And generally, what you're going to do is you're going to compare your p-value to 0.05. If your p-value is less than 0.05, you can say we have evidence against the null. There seems to be an effect. Reject the null hypothesis, whatever else you want. I'll talk about that next week. You're not going to have to do it for homework this week. We'll just keep these things in the back of our mind. We'll learn a little bit about the Cohen's d next week, and then we'll talk about odds ratios the week after. And from there on in, we'll try to just keep effect size on the raw scale by using confidence intervals, and I'll keep repeating that as we go. Probably for you all, the more common effect size is the odds ratio in studies that you guys might be familiar with. And then, what you're going to read about is, do we move beyond this? Should we not use the term? What does it all mean? Right? Or how do we, recommend proceeding? And that's what your two the readings are about. One other thing I'd like you to look at in advance of week 8 when we cover analysis of variance is we will at that point talk about post hoc tests. What happens when we conduct multiple statistical tests on the same data set? Do we have to adjust our alpha level? And the answer to that is yes, but sometimes no. So there's not hard and fast rules, but that information is in Dr. George's text, pages 49 to 56, along with a bunch of this stuff too. So we'll refer back to this in week 8. So last thing I want to do is show you the strobe guidelines, talk about your homework again, and then we're good. But does anybody want me to talk about any other thing that we went through now? So highly conceptual week, obviously. But the good news is you don't have to do any computing. There's no SPSS required this week. It's just a few questions about some of this stuff, some scenarios, and then really a big part of the homework is reading the Beyond 0.05 article. So again, as you said before, this one. And then if we go into, so again, to remind you, there's no readiness quiz. You will have one next week. So it's just the homework assignment this week. Whoops, let me look at the student view. Hold on. It was pretty good. So the first thing it's actually going to ask you to do is to look at what we call the strobe guidelines. Right? Strobe stands for Strengthening the Reporting of Observational Studies in Epidemiology. You only have to download one of these things. It's a checklist. This is the one you want, the one that covers cohort, case control, and cross-sectional studies combined. So I'll just open it up for us and show you what it has. So it basically takes you through what should be in a research report, which is just handy to keep around. You're going to want to look at sort of the results part. It's not long, right? I would read through the whole thing, but you're going to, part of your homework is to discuss some of this stuff here. And we're going to get in the habit of this part, main results, reporting results starting next week. When I say summarize what you did, is to give confidence intervals for effects, other things that are on this report, summary statistics of the participants, so on and so forth. Okay. So if we begin, for example, basically just asking you something. Canvas has been slow today. There we go. List 2 items you feel are key in reporting a rigorous and reproducible manner, with a brief explanation of why they're important. So for that, I think the thing to do is to look, in the method and results part. Ask you a bunch of stuff about power, a couple of things about some biases, and then towards the end here is, this is, again, answering this question, you'll need to look at the world beyond P less than 0.05 article. That's where the ATOM acronym is discussed. Okay. Alrighty then. So that's it for this week. I'll grade your homeworks tomorrow. We'll go ahead and keep next week as planned Zoom. And then we'll try to pick up week 5 in person. Sorry about tonight, just happened to be, wasn't able to do that. So yeah. Any other questions before we adjourn?